So now we're at the stage of power estimation. And power estimation is a critical part of the design and analysis process. And just like everything else, it really opens up a whole new can of worms. Okay, standard cells and other macros have power information inside them. They're provided inside our .lib files. Okay, and what does this include? There's basically three types of power. Switching power is the energy consumed by charging and discharging an output load. So the switching power is different for each timing arc. So that's our basic dynamic power. That's whatever it takes to charge and discharge the capacitors, which are the loads of the gate. That's the switching power. And so again, our lib file will show for each timing arc a function of how much the load is, what our power consumption is going to be. But there's also something called internal power, which is the energy consumed due to switching of internal nodes or short circuit power independent of the output load. And this can depend on a pin toggling and or a specific timing arc. So there's actually two types of internal power. One's like input related and one's output related. But in general, if we have, for example, let's take a buffer. So a buffer would be made of two inverters. The internal power would mainly be the power that takes to charge and discharge the internal node between the two inverters. With something like a flip-flop, there's a lot of internal power that is spent due to clocking, even if we do not change the actual input. So that would be, so internal power can actually sometimes be dominant. Okay, and finally we have leakage power, and that's the power consumed by devices while they're not switching, and it depends on the state of the inputs or internal nodes. And we'll now use this information to calculate the system power consumption, and we will see a differentiation between these three categories in our power reports. So now we're going to briefly go over the types of power calculation, and this is another somewhat confusing one. We're going to use Cadence's power analysis tool, which is called Voltus, and it differentiates between static power analysis and dynamic power analysis. And while this may seem straightforward, it is not, because when they say static power analysis, what they mean is they're calculating an average power or current per cell. That means we're going to get one number of the power that is consumed per the cell, even though we'll see in a second that it actually may be under dynamic conditions. On the other hand, when they say dynamic power analysis, what they're talking about is a power or current waveform per cell. So each cell is going to show us the actual waveform of the current or the power consumption over a period of time. And dynamic power analysis is much more heavy in a calculation-wise and also storage-wise than static power analysis. So that seems straightforward, but it isn't, because both of these, both static and dynamic, they have what is called vectorless and vector-based. So when we take a vectorless one, it means that we're having average activity factors. We're assuming that all of the inputs or all of the flip-flops or something like that are toggling at a certain activity factor, like say 20% or something like that, which is a very, very, very it's very inaccurate. On the other hand, we have what is called vector-based, which means that we have to go and run an actual simulation and then take the actual movement of the different nets. So how many times or at what time point a certain net was charged or discharged, and then use that to do this dynamic or static power analysis. Okay, here we're only going to be running static analysis to calculate power, and we're going to do it at the vector-based way. What we did basically before was using a vectorless, which is very, very inaccurate. So let's discuss vector-based static power analysis. After synthesis, we ran the report power command. And how did the report power command know what our power was? Well, it looked at the create clock command that we had in our SDC to control the clock toggle rate. So that was the frequency inside our power calculation. And there is a command called set switching activity, which can be used to control activity on specific nets, like primary inputs, how often we say they toggled at an average, like 10% or 20%, we toggled the inputs. Clock gates, how often they toggled or not. And sequentials, because the standard cells aren't going to be changing every single clock cycle. And if we did set switching activity, which we didn't, we just used whatever the default was, we may be able to somehow calibrate it to what is actually happening in our design. But it probably is not going to happen. Once we do this, we really get propagated activity, or just globally decide that every single net is switching 20% of the time. And that is really, really, really inaccurate, even though a lot of people don't go beyond that and assume that whatever they hit in report power was a real number, but it really is not. And that's why we should really go and run actual activity from a simulation. So what we're going to do is during our simulation, we're going to write an activity file, and Voltus supports these 5 types. The 2 main ones are VCD and TCF files, where the big difference is that a VCD file really shows for every time step which nets changed from zeros to ones or to X's or to Z's, and TCF counts for each of the nets how often they toggled. So this enables us to do a pretty accurate power estimation at a much, much smaller file size. VCD files are very, very heavy, but you can't use TCF for doing something like a dynamic power simulation. So what we're going to do is, after we created this activity file, we're going to read in the activity file with the read activity file command, and then calculate the actual energy consumed in every net with report power. So again, we are going to, first of all, dump our activity file, the VCD or TCF usually, from our simulation. And so VCD is the value change dump file, and it contains all the signal changes in the simulation. How are we going to do that? We're going to open a database inside our inside Xcelium, which is a VCD database, and then we're going to probe our signals with a certain depth, and we're going to write them out into a design.vcd file or something like that. Right? Okay, so that's for VCD. TCF is kind of similar. It uses a dump TCF command, and then it runs the simulation for a certain amount of time and ends the dump TCF. So these are 2 possibilities. You can also, again, do other formats. Okay, after this, we're going to open up Voltus, and we're going to read in the activity file and report power. So we're going to run Voltus minus stylus to open up the tool. Then we're going to restore our design with readdb. We're going to use this read activity file to read our VCD or our TCF file, and then we're going to do a report power with the static method, and we're going to look at our out file. So let's go and see that in the demonstration. So I told you that we didn't look yet at the script of the back annotation. So backannotation.tickle over here is a bit different than the script we had previously, and let's see why. Okay, what it's going to do is going to now do a little bit kind of other things over here. And the first thing it's going to do is open a VCD database and start probing signals and dumping into it. So database minus open the VCD file that we set up for VCD, and then it's going to do probe.create. It's going to write all of basically our signals to a deep depth of the hierarchy. We only have a single hierarchy, but still it's going to write all of the signals into this, and that's going to create a VCD file. There is another option. I have it commented out here, which is a TCF file. That's a cadence toggling format, but I'm not using it in this case. So once I open the VCD file, I run my simulation, and it's going to write out all of the signals and all of the toggles into the VCD file. So let's see what actually comes out of that. My VCD file was written out to the export directory, and we see here that there is this file smtb.vcd. So we can look and see that it was created, and it shows for each and every single one of the wires what happens to it in some sort of a text type of a way, the different standard cells and so forth, what is going to happen to them. This is not very readable to the naked eye, but it is readable by the tool, and it really shows for each and every single net and every single cell what is going on when there were toggles, when things changed. So that's the VCD file, and we're going to use that in order to evaluate the power. That is a bit different than the TCF file, which, if we had written it out, all it's going to say is that each and every one of these cells, what the average time, the average number of toggles it did throughout the entire simulation. So now that we've run timing back annotation and created our activity file, in this case we used a VCD file, but we could have created a TCF file or SAIF file or one of the other formats. What we're going to do is estimate the power consumption that we actually consumed during this simulation under this specific test bench, under this specific workload, but it will give us a pretty accurate evaluation of how our system is going to work. And for that, we're going to use Cadence's voltage analysis tool, which is called Voltus, but we could have also run this under the hood of Innovus. I just want to demonstrate it with Voltus. So what we're going to do now is in our command line write Voltus, but not only Voltus, we're going to write Voltus minus stylus, because this is using the stylus common UI approach. And here Voltus is loaded and has also opened up our UI, which in this case, we are not going to look at the UI right now, so I'm going to minimize it. Later, I'll show you what we can see in it. The UI is very similar, if not the same, as we saw in Genus, and we will see extensively in Innovus, and we could also look at in Tempus. So I'm going to minimize that, and I'm going to go back over here and open my script, and I have a script for running this post-synthesis power analysis within Voltus, and it's called Voltus post-synthetical. Okay, it'll be a little bit different than running it at other times, and there are more things that Voltus can do other than just this power analysis, but that's what I'm going to show you right now, or this power estimation. So as you see here, it says make sure you ran Voltus minus stylus, because this script will not work if we don't add the minus stylus, which we didn't need to add in Genus because it by default loads in stylus. So we have our setup, which is just going to set up our design by giving the top level name and loading the procedures, the defines, the settings, all of the files that we actually already loaded before in Genus. So I'm just going to load those. Okay, and I see that everything looks okay over here. I didn't get any errors, so that's a good thing. And now what I'm going to do is restore the design that we saved out of Genus, and that is in the DBs directory over here. We had a database that we stored out into the post-syn directory. All the files that we need actually to reload the database within Voltus are here, and we did that by adding some flags in our Genus command. I can show you that quickly. So here at the end, what we did is we write out a database for loading in Innovus, Voltus, and Tempus. We wrote write design minus base name with the design name, which was actually pointing here to the DB's post-synthesis. But we also wrote minus Innovus minus DB, and that wrote out this entire directory with all of these files. So now we can go back to the Voltus script, and we can just run readdb. And when we run readdb, it's just going to load our design exactly as we left it at the end of synthesis. And finally, we have our Voltus command line. So I told you before that I was going to go back to the UI. So I'm going to reopen the UI. And now what I see here is I actually have standard cells. Like I have the state regs, and I have different types of cells over here. This is an inverter and all kinds of things. I can also open the design browser over here, and that enables me to kind of look through my my design over here. So you see I have my terms. Those are my pins, and I can see where my pins are, like where the overflow pin is over here, and I can look at different nets. I don't have my routing right now, but standard cells I can look at where count reg 2 is over there. I can do a lot of stuff with this nice little window over here, and it also tells us the name of whatever we want over here, which we can later on use in scripts or use in the command line to do all kinds of operations. So I see that my design is loaded into Voltus. So I restored my design with the readdb, and now it's loaded into Voltus, and now I can start my power estimation. So the first thing is what we're going to run is known as static power analysis, even though we're doing this with a vector, so it's in a way dynamic, but this is what Cadence calls it. And so we do setDB power method static, puts us in the static situation, and that's important because dynamic power simulation is a bit different. It takes a lot more time to run. So what we're doing now is we're just seeing how much power is consumed during our simulation, and that's with the static power analysis. Okay, there's another thing that's going to report missing nets. It's going to give us some sort of a log file that's going to tell us what nets were not annotated. Then we're going to have these analysis views that we're going to set for our power analysis and in general what our setup, hold, leakage, and dynamic are. So we're just going to use the selected power analysis view and for all of that. And our selected power analysis view in this case is our worst case corner. That's what we selected in our defines file. Okay, so now we have our view set, and the next thing we're going to do is to reset the activity file. That's just done for cleanup. And the important kind of operation over here is read activity file minus format VCD, because what we stored was a VCD file, as we saw before. The scope is the test bench name dot DUT name, that's how our DUT, our SM module, is stored inside the VCD file. So you have to make sure you've got the right hierarchy here, otherwise you won't get any annotation. Okay, start and end means that we don't have to look through the whole VCD file. We can actually only focus on a certain area of the simulation. So if we did different operations, for example, during the simulation, we could put a window of start and end where we want to measure the power for, and then we give the VCD file itself. So that's what I'm going to run now, is this read activity file command, and it finished successfully. That read our VCD, and what I can do now is to report the power. So I do this report power command. Okay, so it did the report power command, and it says the output file is over here, as we see here, under report synthesis power. Okay, so I'll go over and look at that. Reports, synthesis, and the power report. This is what was spit out by the report power command. And what I see here is Voltus made this on the design SM. The libraries used, okay, the views that are used: worst case analysis view for dynamic power, the worst case analysis view for leakage power. And the switching activity file used shows that we use this sm.tb file. Okay, the window was from 0 picoseconds to 1500 picoseconds. That's what I chose as the start and end times. Okay, and the annotation coverage, and this is the most important thing. If we got the scope right and we had all of the cells and nets inside our VCD file, then we will get 100% annotation coverage. If we got something less than 100%, we should check it out. Sometimes you will have a little bit less than 100%, and I guess it could come from all kinds of different reasons. But if you get 0%, that means your scope was probably wrong, or something else went wrong with reading the back annotation, reading the VCD file or the TCF file. But this is what we want, the 100% annotation coverage. Okay. So we get this table over here, which has all the cells in our design. These are the instance names. These are the, the base cells, the type of standard cell that was used. And we have several categories of power: internal power, switching power, total power, and leakage power. We expect to see, and we do see that the leakage power is going to be several orders of magnitude lower than the dynamic power. But this is also important to look at. If we had a design that was just sitting there all the time and not toggling at all, then the leakage power would actually become dominant. So anyway, what we see is that all of the top power consumers are registers, and that could be expected. The flip-flops, when they do their toggling, they have a lot of internal power, whereas other cells have barely any internal power, and they have a lot of switching power as well, so their total power is much higher. In fact, they're like an order of magnitude or more higher than the other cells in the design. When we go to place and route, we'll see that we'll have clock buffers and so forth in this type of an area. Some registers will be sitting there dormant the whole simulation, and therefore they won't be toggling at all, and you might see them way down in the list. But we need to know kind of what our simulation is doing, understand by the names where these registers are, and as a sanity check, and just to understand what's going on, make sure that we do see why certain cells. Again, it's easy to tell what registers are. Sometimes it's harder. We have no clue what this G592 is, right? But it's easy to see what kind of registers there are, or what a clock buffer is, and realize that it makes sense that they're consuming more power than other cells. So this is a type of a sanity check. And again, this plus this pretty much is going to equal the total power. The leakage power is much smaller, so it doesn't really move the needle over here. When we do go down to the end of our table, we'll see a summary over here. And as you can see, there were 47 cells altogether that were consuming power, and the internal power, switching power, total power of the entire simulation, and the leakage power of the entire simulation. Also, we can see the total capacitance, which doesn't mean much at this point when we're post-synthesis, but post-place and route, it can tell us how much the wire capacitance of our design is. So that's how we kind of looked at power. Another thing is that we can look at a more detailed power consumption of a certain instance. So that I will do report inst power, and I choose an instance, so I can choose, let's say, some inverter that I have, like G604 is an inverter, okay? And it will tell me what's going on here. So it tells me everything about it. It says what the instance is, what type it is, what the internal power, switching power, and leakage power, which should be the same as in our table in total power. But it tells us really how all the different parts of it. So you see duty, density, cap, rise, flow, etc. The leakage power at the different cases that we would see inside the SDF or inside our lib file, the different parts of it. So we can really explore a certain instance in this way. To summarize, in this demonstration we covered the motivation for gate level simulation, running zero delay gate level simulation, back annotating timing information from synthesis to simulation, and then running a gate level simulation with these applied delays. And finally, writing out activity information, which is usually a VCD or a TCF file, and using Voltus for vector-based power estimation for a given workload, which is usually a typical type of a workload. And remember, this is called static power analysis in Voltus. The power estimation that we ran is much more accurate than the vectorless analysis that was run at the end of synthesis without a vector. Finally, I just want to point out that we demonstrated this at the post-synthesis stage, but everything that we saw here is applicable throughout the place and route, and it's even applicable at sign-off. So basically, we can go and run place and route, then extract our post-place and route net list, our extraction, so we get the SDF with accurate timing with routing and everything, plug it into our simulation, run gate level simulation, and then come back with our VCD or our TCF file and run post sign off level power estimation.